The overall goal of our project was to implement weapon detection in real time with the Intel OpenVINO starter kit. To achieve our goals, firstly we choose and curate already available datasets for our purpose. Next, we choose the right architecture of CNN. Then, we use FPGA. A major advantage of FPGAs over GPUs is the low latency operation. GPUs can achieve high throughput in terms of frames per second, but it often comes with the cost of increased batch size and thus increased latency. Finally, we connect our detector to Twitter in order to show an alert to the final user. During this presentation, we will highlight the key figures of our neural network training and the advantages of Intel FPGAs. Neural networks are algorithms that imitate the human brain so as to recognize some patterns. We will work with images in this project. As you can see, it consists of some neural layers. The input is your image and the output is the prediction. It could help to cluster, classify, or detect. In our case, it is detection. The first step is to train your model on a labeled dataset. As a human, the model will learn from the truth, so the labels. That's why it is supervised learning. Then you can use this model to compute predictions. Convolutional neural networks are widely used in image and video recognition. Like neural networks, they are made up of neurons with learnable weights and biases. However, in CNNs, all the neurons are not fully connected. In fact, it's local connectivity. Each neuron is only connected to a subset of the input image, receives some inputs, then takes a weighted sum over them, passes it through an activation function, and then gives an output. The aim is to reduce the number of parameters in order to be more efficient. Whereas, to obtain good predictions, neural networks must be trained on a huge dataset.
To have a sufficient number of training data, we had to fusion multiple datasets. We were able to find some datasets on the internet, but many were not annotated. For the training, we need to have the GAN bounding box annotations. These facts reduce the number of actually usable datasets to 4, which are on the slide. The fusion process consists of converting the annotation bounding box information into a format adapted to our framework, to merge the datasets in a random way, and splitting it into a training and a validation set. At the end, we were able to collect 5,400 images, which is not a huge number. To have more images, we have trained another heavy neural network, which is YOLO v3, with the training set, and a script which passes unannotated images through the network, shows the user the identified bounding box, and lets him quickly choose if he saves the labeled image or not. Unfortunately, we didn't use this as it needed sufficient time to have a huge number of images. You only look once, YOLO, is a real-time object detection architecture. To perform an image detection, some networks have one part dedicated to region proposal and another part dedicated to classify the proposal. This method is accurate, but can be very slow. YOLO is different. It combines the two tasks in one single network. This network divides the image into regions and predicts bounding boxes and probabilities for each region. These bounding boxes are weighted by the predicted probabilities. The major advantage of this network is that it is really fast. It is perfectly adapted to our situation where we don't have a big GPU to perform the calculations. We also tested in this project the tiny YOLO v2, a small network based on YOLO v2, which is less accurate but way much faster. This TensorBoards visualization allows us to see the tiny YOLO network size in comparison with the standard YOLO. To use these networks, we have used Darknet, which is an open source neural network framework.
This is the curve of the IOU, intersection over union, during the training. With a learning rate of 0.0001, the IOU is rising. The darknet framework takes batches of 64 images. The OpenVINO framework offers us many possibilities. As we use darknet, we convert it into TensorFlow protobuffer file with a custom script. Then, we run the model optimizer to generate intermediate representation data. This AR data is used through the FPGA and CPU plugins. In details, we run the foldbn.py script to fold the batch norm layers into the previous convolutional layer. Then, the YOLO2tf.py script to convert the config and weight files into protobuffer file. Finally, we run the model optimizer to generate OpenVINO AR XML. Let's talk about hardware now. The desktop computer has an Intel Xeon CPU. The OpenVINO is connected through PCI Express and is composed of Intel Cyclone 5 FPGA. The camera is connected through USB 2. The FPGA has 301,000 programmable logic elements and 342 DSP blocks. As we use this FPGA as an accelerator, we parameterize it according to our needs. We use the convolutional PE array to accelerate the convolution, parametric ReLU primitive to accelerate ReLU and leaky functions, and maxpool primitive to accelerate maxpool. Here are some parameters of the convolutional PI array. We define K vectorization, which is the number of parallelized filters, and C vectorization, which is the number of parallelized channels. As you can see on the slide, we reach quietly the optimal abilities of the FPGA. As intended, the YOLO-V2 has a good map, that is to say mean average precision, because of its size, but terrible FPS and bad latency. In contrary, the YOLO-V2 Tiny and our custom fast implementation of YOLO-V2 Tiny have very good FPS and latency, but lower map. The latency for detection is only 2 seconds. It's very low compared to 11 seconds latency for Twitter to post our tweets through the API. Now let's test. The GPU inside the computer is for the screen only. We use a real CCTV footage to demonstrate the ability of the whole system to detect firearms and send a tweet with a picture of the scene. The webcam, feeding the YOLO network with images, filmed the YouTube video on the screen. Without the FPGA, there are only 10 FPS with a 1 second latency with tiny YOLO-V2. With the FPGA, there are 24 FPS and a negligible latency with tiny YOLO-V2. With the full YOLO-V2, there are 4 FPS and a 2 second latency. However, it's more precise as the two guns are both detected.